Hey everyone, so once again, we're going to start off with doing a bunch of these practice questions. Same idea, just put your answers on a separate sheet of paper. If you get the question right, you don't have to watch the video. You can just move on to the next one. Unless you want to see how I explain going over it, or you want to hear some maybe information that you might not have known that I kind of throw in during these explanations. So we'll start with the first one. So pause video work itself. I'll go over in a second. All right. So the first question says, what does the acceleration graph versus time look like for an object that is falling towards the Earth? Um, for the most part, one thing that we're going to talk about is that the acceleration of an object falling is constant. It doesn't matter when or where you drop it, as long as you're fairly close to the surface of the Earth, the acceleration is always going to be a value called that's 9.8 meters per second squared. So the graph will look like this. Now, if you didn't know, don't worry. We're going to end up going over it when we start talking about linear motion stuff. Free fall stuff. All right. Here's the next question. Pause video, work itself, and we'll go over in a second. All right. Now, the question says, at which point is the acceleration the greatest? Now, what we have to do is we have to pay attention to the graph. This is a position versus time graph, which means we're not really looking at slope. If we're looking at slope, that would tell us velocity. One thing that we have to realize is that when we have a position versus time graph, the curve of the graph tells us that we're accelerating. And the more of a curve we have, the more the object is accelerating. So really what this question is asking for is at which point is the curve the most? And it curves the most at E. This is confusing. Choice D, which is letter E. All right, here's the next one. Pause the video, work itself. We'll go over in a second. All right. They want to know what the total distance is. Now, this is a displacement versus time graph. So at first, you might think, okay, we just have to read the graph. We're not doing a slope, we're not doing an area, because slope gives us velocity and area gets us nothing for this graph. However, the key thing here is that it wants the distance. This is a displacement graph, which we know can go up or can go down. Distance does not. So what we want to do is during each segment, think about how much distance is covered. In the first segment, 8 meters is covered. In the next segment, nothing is covered because it stays at that same location. Uh, During the next 2 seconds, we have another 8 meters covered. And then in the last 2 seconds, we have another 8 meters covered, this time going backwards. In displacement, these two eights would cancel out, giving us the displacement of 8. But because this is distance, we're just going to add all 4 of these terms together to get 24. All right, here's the next one. Pause the video, work itself. We'll go in a second. All right, so here they want us to figure out what the average speed is during the first 4 seconds. This one is pretty straightforward. We're going to use the taboo equation, mostly because of the fact that they do specify that they want average speed. So we start here. During this segment, we walk 8 meters. This segment, we go 0 because it's a displacement. I need to clarify this. So the total distance covered is going to be 8 meters. And they do this in 4 seconds. So that should be 2 meters per second. Now, one thing to point out is if this question wanted to know what the average speed was during this full 8 seconds, then you have to remember that you have to pay attention to whether this is speed or velocity. And because it says speed, we would have had to do 16 divided by 8. Or if this said velocity, it would be 0 divided by 8. So pay attention to these types of questions, whether it's saying average speed, average velocity, because this is really the only equation where that distinction will end up mattering. Here's the next one. Pause here, work itself. I'll go in a second. All right, this one's a little bit on the trickier side. It wants to know at which value of t will the cart be back at its starting point. Now, this is a velocity graph. So back at the starting point basically means that the displacement ends up being equal to 0, or the final position is equal to 0. But the displacement is 0, and we get displacement by looking at the area. The only way for the area to be equal to 0 is if the area above the curve, so this section, is equal to the area below the curve. So what I can do is I can actually get rid of a few choices, like this is going to be wrong because during the first 5 seconds, the graph is always above the 0 axis, so the area is going to be positive. I could also get rid of 2.5 for pretty much the same reason. And 3 seconds. Wow, I can actually get rid of all three choices, and I'm left with 8.5. Now, if they didn't have all three choices canceled out, what we would have had to do is just essentially check to see if this area down here of this trapezoid and this area of the triangle above the line, if those were equal. So if they had said 11 seconds, we would have wanted to check to see if this had the same area as this before we made our choice. But for here, that was kind of the main idea, was to realize that the graph above must be equal to the graph below in order for us to have a displacement of 0. And the reason for this is because when we do the area, right, so the area of a trapezoid would be base 1 plus base 2. If you don't know the area of a trapezoid, that's fine. You could have just done the area of a triangle plus the area of the rectangle. But when you do this, the height of the trapezoid is going to be negative 20. So that's why the area will end up being negative, because the velocities are negative. All right, here's the next one. Pause video, work itself. I'll go in a second. So this goes back to the graph before. It says in which direction is the car traveling at 4 seconds. Now this one we have to be careful of. So at 4 seconds, is right here, the graph is going down. So a lot of people might say, okay, well, since the graph is going down, it must be returning back to where it was. But that's not the case. Remember, this is a velocity graph. Velocity graphs, the sign of the velocity is telling us the direction we're moving. Because this graph is still in the positive side of the velocity graph, the velocity is positive, meaning it's still going to move in the positive direction. So it says before that the car starts moving northward, so it's going to be moving northward this entire time. It just happens to be slowing down by this moment. It doesn't switch directions until after 5 seconds, when the velocity graph goes under the line and becomes negative. So this entire section right here, it is moving north, and it's only this section where it ends up moving south. Yeah. So the direction is still north. All right, here's the next one. Pause video, work itself, and we'll go over in a second. All right. So again, we're looking for the interval in which the object is accelerating. Again, acceleration for this means that it's a curved graph. So the only section that kind of looks like it's curved is right here. So from 3 to 4 seconds. So one thing you want to keep an eye out for is this kind of idea of the relationship between what a displacement graph should look like when there is an acceleration. So you need to be able to recognize that. And again, just as you saw before, things like the more it curves, the more it accelerates, that type of connections. All right, here's the next one. Pause the video, work cell phone, go in a second. All right, so we want to know which car is accelerating with a non-zero acceleration. Remember, we always deal with constant acceleration in this class, but sometimes that acceleration could be either 0 or non-zero. So they're saying that it's actually accelerating, which means these two, this one and this one, I could throw out because they're both linear. Now, between choices B and C, it might be a little bit tough of how do we know which one is the accelerate, like both these are curved, so they're both technically accelerating, and that is true. The one thing though is that it's saying that it's in a straight line, which is implying that it's only going in one direction. So this is the only one where that's happening. This one, it is technically going forward and then coming backwards, right? In order for us to have the distance kind of coming down. Also, technically, distance can't actually go down. So there might be a whole lot of other issues with this graph, but that's I think the idea that they wanted was this wasn't a straight line. This one just doesn't really make sense, and it's technically going back and forth in two different directions. All right. All right. Here's the next one. Pause the video. Works up. We'll go in a second. All right. Well, because this is a linear line, we know that the velocity is going to be constant for this because the slope is constant. So the graph of velocity is constant. And because the velocity is constant, we know the acceleration is 0. So it must be 0. Here's the next one. I think this last one actually. Pause video. Cell phone going in a second. All right. So they want to know which car has the greatest acceleration from 10 to 15 seconds. Because this is a velocity graph, the acceleration is the slope. So it's really asking which one has the greatest slope during the 10 to 15 seconds. And the greatest slope is car D, this one. So there you go. All right. And that's it. So like I said, you want to be able to recognize, what aspect of the graph are you looking at? Are you looking for slope? Are you looking for area? And you almost want to get into the habit of changing out the words. So just as I did here, where I crossed out the word acceleration and I wrote slope because that's what they're really looking for. Um, Up here, where was it? Okay, over here, uh, you know, denoting, what exactly do they mean when they say coming back to the starting point? The fact that they mean the displacement is zero, or therefore the area is zero. You know, these types of little things, recognizing them and then putting them down on the paper to help kind of direct your attention and direct your focus one doing the problem can really help you elevate your work in this class and make it so that you end up doing a lot better on these types of questions. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.